Hey HMS modelers, this is Mike Bartles from the Hydrologic Engineering Center. In this video, I'm going to introduce loss methods within HMS. So this video is part one in a series of videos that is devoted to simulating losses and excess precipitation within HMS. This lecture is meant to serve as an introduction and will not be an exhaustive, detailed look at all the various options that are contained within the software. So we won't be deriving equations or even delving into too much math. Instead, we're going to focus more on concepts and how losses are accounted for within HMS. Let's begin by taking a look at the hydrologic cycle, which begins with the evaporation or transpiration of water, which can occur from the land surface, from vegetation from lakes, from rivers, or the surface of the ocean. As moist air is lifted, it cools and water vapor condenses to form clouds. Moisture is then transported around the globe until it returns to the surface as precipitation. And precipitation can fall in multiple forms like rain or snow. Once the water reaches the ground, one or two processes can occur. Some of the water may evaporate back into the atmosphere or be transpired by plants, or the water may penetrate the surface and become groundwater. Groundwater either seeps its way back into the oceans, rivers, or streams, or is released back into the atmosphere through evapotranspiration too. So the balance of water that remains on the Earth's surface is runoff, which empties into lakes, rivers, and streams and is carried back to the oceans where the cycle begins again. This is the hydrologic cycle broken into a logical set of steps and included within HMS. So these processes are all simulated to varying levels of detail within the software. It's pretty complicated, huh? Don't worry, we're only going to focus on the processes located in the center of this image. Other lectures will discuss additional processes, but all of these processes work together to estimate the discharges from a watershed. A hydrograph is a graphical representation of discharge with respect to time. In a hydrograph like this is a result of the runoff process, which is comprised of overland flow, which is direct runoff, interflow, which is flow in the upper soil layers, and groundwater flow, which is saturated flow through alluvial deposits or other water-bearing formations. So in this set of lectures, we're going to pay particular attention to direct runoff, which is shown here in red. As you can see, this volume is primarily responsible for the peak in the runoff hydrograph. So water that is lost due to infiltration can still contribute to the total runoff hydrograph in the form of slower responding interflow or base flow. These volumes are also accounted for within HMS, but we're not going to focus on them within these lectures. A key element for the simulation of the precipitation runoff process is the determination of the portion of runoff that contributes to direct runoff. Direct runoff is the portion that enters the stream quickest and contributes the most to peak discharges, as we saw in the previous slide. And this portion of precipitation that leads to direct runoff is called excess precipitation. The difference between precipitation and excess precipitation is defined as loss. So let's look closer at these loss computations within HMS. The principal loss components are interception and canopy storage, surface and depression storage, and infiltration and soil storage. Precipitation that is captured and stored in either the canopy, surface, or soil layers can be evaporated or transpired back into the atmosphere. Precipitation that exceeds the storage capacity of these layers becomes excess precipitation. So as a review, in this video, we introduced loss simulation within HMS. So as we discussed, there are three ways that precipitation can be lost: due to the canopy, the surface, or through infiltration. In HMS, you have the option to simulate all of these processes, two of them, one of them, or none of them. Within the next two videos in the series, we're going to look more closely at how canopy, surface, and infiltration processes are simulated and go into a little bit more detail. So thanks for tuning in, and I'll see you in the next one.